Hiya, humans. Happy Monday. I hope everyone is having a fun Monday. It's the last week of class, so I hope you're all as excited as I am. Only 5 more days, and then we're free. Well, kind of. You also have to do final exams. Well, most of you. And then I still have to grade all that and then do the submissions. But whatever. We're super, 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 super close to the end. I hope everyone is as excited as I am. So, some key notes, or not notes, some announcements for today. One, announcements. One is that evals. I kept talking about these, but I still haven't sent an email. I probably should have sent one, hopefully or I should send one today on Monday. Please fill one out. Please fill out. Because it will help me get another job. As most of you know, I am not teaching over this summer and I am not teaching next semester because technically my contract ends and therefore I do not, I cannot teach. So I am not actually employed after this class, kind of. So having good evals helps me be able to get a job. So please fill those out. I know, it takes some time. It's probably like 20 minutes. I don't even know how long they take, to be honest. I know it takes time and you have to think about it. But if you enjoyed my class, please write it out. Also, if you did not enjoy my class, you can also fill out an eval as well. Feel free to also leave notes because I do actually read these. As you notice, I do try to listen to my students and incorporate feedback into my class as much as I can. Obviously, sometimes I'm limited, but I do try to do things whenever possible. So please fill out evals. If you don't want to fill out an anonymous one, because you think if you're gonna do something negative or something and you don't want to affect me for whatever reason, you're also more than welcome to email me instead. But an online the one they have at York is fairly decent. So I'd say please do that if possible. And then I'm looking up if I missed anything. I think there was another thing I needed to talk about. The second thing, as you've probably noticed, exams. We're not finished grading. Not finished grading. I've been trying to update everyone in the Discord as to where we are, what the status of grading for the exams are. Hopefully they'll be finished sooner rather than later. I'm trying to push the TAs to go as fast as they can, but I mean, they have classes as well. They are in stressful situations as well. So they're going as quickly as they can, and I'm trying to help them as much as I can with my limited amount of time. So just note that. Solutions should be up. Solutions are either tonight or tomorrow night. Tomorrow night. So remember, today is Monday. So if you're watching this on Tuesday, then it's not Tuesday. And then tomorrow night is Tuesday. So you'll have that. Another thing for the exams. So as you all noticed, the exam was actually a lot harder than I thought. I had been aiming for it to be under 2 hours. But apparently the average was 6 to 12 hours, and it stressed people out a lot more. So I'm sincerely super sorry for that. As you probably saw from my announcement from last night, I'm going to be altering the grades to kind of compensate for that. The exam should definitely not have been taken that long. It should not have taken that long for people to do. It should not have been that difficult. Sometimes it's hard for someone like me who's used to these problems to figure out what is too hard. And it's almost trial and error, unfortunately, which means this time I definitely learned that these problems are way, 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 way too hard. So I know never to use them again. But unfortunately that means it happened during a horrible time too, right? Everyone's already stressed with exams and everything. So it was so basically bad timing. So I'm super, super, super sorry for that. I will compensate for grades. I wish I could compensate by like giving you all hugs and saying like like actually giving you apologies. But this whole social distancing thing is making it fairly hard. Haven't even left my bedroom in like how many days is it? Last Friday. So it's been 7, 8, 9, 10 days. Um, so it's been very exciting. Anyway, so I'm super, super sorry. And I'll figure out grades for that. Um, and then quizzes. We have a quiz today. You have all day to do it. And then make sure to read the announcement that I sent over the email. 3. We'll talk a little bit about. Do I want to do this today or should I talk about this on Wednesday? Let's wait until Wednesday. Never mind. I'm going to wait until Wednesday for this. Yeah, so okay, that's all the announcements for today. If you have questions, let me know. Yeah, let's start with a little bit of review. So last Friday I went super, super fast. It's so much harder to do this without people actually stopping me and making sure that like being like, yo, Ram, I have no idea what you're talking about. I'm sorry for that. I know life is like, yeah. Anyway, I'm trying. Hopefully it's at least enjoyable and you are understanding things a little better than you would normally. So let's go over some things, right? So we started on Friday with talking about Riemann integrable, right? So it was this big nasty, I think I have it on the top, this big nasty limit, right? Limit as n goes to infinity of the summation of f of xi star of change of xi, yeah? And we decided in order to make this easier to look at, we changed how it looks and we denoted it with this integral symbol, right? So we have the integral from a to b of f of x dx. So remember here, the integral symbol is just a long s. Dx is our differential, so it's a small change in x. And this we call the definite integral. That is a horrible way of writing definite integral. Let me rewrite it. So if you couldn't spell it last time, you can spell it this time. Definite integral. I feel like my writing today is much better than it was on Friday. Do you have those days where like sometimes your writing is better than like other days? Anyway, so today's a good writing day apparently. So then what we did is we talked about the definite integral, right? And we said, what is the definite integral? It's just basically the summation, the area from point A to point B. And we said, well, okay, when can we actually find this summation? And so we had a theorem to kind of help us, and we said, well, okay, if our function is continuous on an interval AB, or if our function has a finite number of jump discontinuities, this is misspelling, discontinuities. No, this is okay. Then the function will be Riemann integrable. That means if our function is continuous, then it's going to be integrable on that surface. And so what we did is we looked at an example. So here's an example. I guess maybe I should zoom out slightly. There we go. So we looked at a simple example of the integral of x squared, right? And in order to solve this, we actually had to take the limit, right? We had no tools to solve this. So remember, we had to find, let me highlight these. So remember how we had to first find our change in x. Why is it so small? There we go. We had to highlight our change in x. We had to find our xi star. We had to find our f of xi star. And then afterward, we found our limit, which eventually ended up, after this whole hodgepodge of a mess, we ended up getting 7/3. And we were like, okay, no, there has to be a better way. And most of you who have already seen this in like high school or some other secondary location, you know that there is a nicer way. And that's using some properties of definite integrals and also the fundamental theorem of calculus, which we'll talk about again soon. So some properties, we looked at 7 different properties of definite integrals, right? And so what we said is we can change variables. It doesn't change anything. the integral from a to a is always going to be 0 because we're not taking any area. We looked at the area of a constant. We looked at what happens if we change the order of a and b, right? If I put b on the bottom, then remember this is changing our area. It's going to be negative, which is kind of weird to consider it as area. But yeah, so you can think of it this way. We looked at multiplying by a constant. We looked at what happens when you add. We looked at what happens if you take an interval from a to b and then from b to c, right? So these are all properties of definite integrals. And these are all things that definitely are highly recommended that you remember for your next class. So a lot of these things we're not going to be using, these things we'll use in this class, but next class, like 1014 is super heavy in integration. Basically, the teacher is going to assume you know how to integrate or what the definition of integration is. And that is why I'm having to do this mini quiz instead of just letting everyone kind of take their grade, because I need to make sure that you can integrate so that you can take the next class. If you do take the next class and you don't know how to integrate, that's very bad. So make sure you do know how to do this in the least. Or at least what the definitions are. Okay, so then what we did is we said, let's make this easier, and we found a way to make this easier, and this was through the fundamental theorem of calculus. And basically what this said is we use this idea, so if we remember in our summations, we had this idea of a telescoping sum. So when we have this telescoping sum, we basically only have to look at the beginning and the end of our summation. And we noticed it almost looks like our limit, like the definition of the integral. We have this xi minus 1. Now, although this is not exactly the same, right? I kind of showed why these are not the same here, because we have different constants in front, so we can't actually cancel. But they're basically close enough that we can kind of make them disappear when we're taking these limits. And this is where we can actually kind of do this. And so what we've basically said is the fundamental theorem of calculus basically says that the integral here, so this integral, is just going to be equal to f of b minus f of a, here, where this big F is just the antiderivative, or is an antiderivative, right? And so we said there's also this other notation here, which I put on the right, f of x from a to b. And so basically, I said it's really weird how this works. But it's super cool, right? Because that's a lot less work that we have to do when we're trying to calculate the integral. And so I don't think many people have seen this video yet. I think because we had the midterm, there's not a lot of people who'd seen this talk. And not many people have had questions yet, so I don't know if there's still confusion about this. But we'll see. So we said, okay, well, we're going to need to know some antiderivatives in order to be able to calculate this. So what are some antiderivatives? So here, I gave some antiderivatives, right? And basically, if you look at any antiderivative, if you take their derivative, you get the function on the left, right? That's the definition of antiderivative. So from here to here, take derivative. So we said, let's look at some examples. And so that's kind of what we started and ended with last time. And so what did we start off with? We looked at this first example, the same one that we just did, where we took the integral from 1 to 2 of x squared dx. So this is exactly what we had last time. And so remember, this is just nothing more than the limit, but we're not going to use the limit definition. We're going to use the fundamental theorem of calculus. And so what we said is this is just equal to an antiderivative taken from 1 to 2, because 1 to 2 are our limits. Are our limits, right? 1 and 2 are our limits. So we go from 1 to 2 of an antiderivative. Here, if you look at this very top one, our antiderivative is just x to the n plus 1 over n plus 1. So here we get x cubed divided by 3. Can I remove this? Yes, cool. And so what we do is we just literally plug in. We get 2 cubed minus 3 minus 1 cubed over 3, right? So first we do f of 2 minus f of 1. And so this we get 8 minus 1 over 3, so we get 7/3. So notice how this is exactly the same solution that we found with our method of limits. But this is significantly easier to handle, right? We don't have to do all these nasty limit calculations. We just take an antiderivative and plug in. That's so much nicer. So let's look at another example. Here we have the integral from 2 to 4 of 2x dx. So one of the properties is we can pull this 2 out, right? And so I have the integral from 2 to 4 of x dx. So remember here that these are all within parentheses, right? So it's 2 times all of this. And so this x, right? This is one of our functions. So we know that it's x. You add 1 to the exponent and divide by the new exponent. So we get x squared over 2, right? So here we have x squared over 2. And we take this from 2 to 4. Notice how I have this bar here, right? So this is telling me what I'm plugging in. So first I plug in 4, then I plug in 2. So I have 2 times 4 squared over 2 minus 2 squared over 2. So this is this is f of 4 minus f of 2, right? So here we're using the fundamental theorem of calculus. And then here, actually, I don't know why I put these on the side like that. But let me put these. Why is it grabbing the 2? I just want... There. No, bananas. It hates me. No. Why? Okay, I give up. Anyway, what we want to do... There we go. And then we'll grab this underneath part. Oh, definitely not happening. Bam. Okay. So what we have is we just plug it in and we just solve. So we have 16 over 2 for this left hand, and then 2 squared over 2. So 4 over 2 is just 2, right? So this is 4 over 2. So we get 16 over 2 minus 2, so 8 minus 2, and everything is multiplying by 2. So it's 2 times 6, which is just equal to 12. Okay, so let's try something a little more complicated. Let's try this problem, where we have sine of x dx from 0 to pi. What's the area? So sine of x, if we notice, we actually already have this in our function list. So this we already know. We know that this is equal to the minus cosine of x, right? But here we're taking the integral from 0 to pi, right? And so here I just need to plug in, so I get minus cosine of pi. I'll put these in parentheses, minus the minus cosine of 0. Notice how I have 2 minuses here, because I am always taking this minus in the middle, right? Because here I have f of pi minus f of 0. And my f has a minus in it, right? So here I have a minus. So you have to remember these things sometimes when you're looking at things with minuses. So what do we get? What's cosine of pi? Well, this is just minus 1. Yeah, it's just minus 1. So we get minus 1. These minuses, they're just plus, right? So I'm going to make this plus. And then cosine of 0 is just 1. So here I get 1 plus 1, which is just 2. And that's it. So the sum of sine of x from 0 to pi is equal to 2. So if we look at this, right, here is sine of x, right, from 0 to pi, this area here is equal to 2. That's pretty cool, yeah? Okay, so now let's look at a fourth example. Now, I want you to think about this for a second. How would you try to solve this? This one here. How would you try to solve this? one thing you're going to notice is none of these functions are present in my list above. So what do you think is going to be used? One thing you should notice right off the bat is I've kind of given a hint, right? The hint is this. It's that my line here is super small. So my answer should be something small. Okay, well, if it's small, this means something is weird, right? So let's actually look at my properties from before and see if we see anything that might help us. So here we have these properties. And me personally, I see something right away that is very helpful. And that is property 2. That if I take the integral from some number to the same number, then I'm always just going to get 0. And if we look at the example that we're just talking about, right, I have it from 5 to 5. So since they're the same, that means I'm taking the area of nothing. So this is just 0. So even if we have this big, long, complicated thing, that no one wants to do, and in fact that we don't know how to do, right? We don't know how to find the antiderivative of this, but it doesn't really matter, because at the end of the day, we see that it's going from 5 to 5, and therefore it doesn't matter. So it's something to note that sometimes if you see something complicated, it's not because I want you to actually solve it, it's because I want you to find some other way to solve it, something that's easier.